On one hand, we trace the history and formation of the Milky Way galaxy by targeting the satellite galaxies that helped form the Milky Way during early stage of the universe. The stars there are very old and high value, but the problem is that they are far away. Only a tiny portion of light reaches our telescope, so they appear to be very faint. On the other side, we aim to profile the dark matter halo that is believed to be enshrouding the Milky Way as shown in the figure. Therefore, be able to see much more stars within the same amount of time and be able to see much fainter stars help tremendously. The Subaru telescope can see fainter stars because it has a huge mirror and thus collecting more lights. And the spectrograph has a wide field of view, which can cover much larger area in sky and see more stars. So in short, this $80 million is a must and best for our task. One of the great challenges of designing the survey is determining exactly which astronomical objects should be observed with a spectrograph and how long each should be exposed. The longer the exposure time, the stronger the signal to noise ratio, which gives us more information about the star. But we want to spend it on good stars. We want to spend it on high value stars as time is the most expensive factor. For example, when we target the satellite galaxy, we typically observe the luminous red giants in it. The figure on left shows their size compared to the sun on the log scale. However, when we observe the giants within the Milky Way, we see lots of dwarf stars, which happen to look the same. Although there's like a huge difference in their size and the surface gravity, they're both red, and the further away giants will look smaller and fainter. So inevitably, we will observe large portion of dwarfs that are not member of the satellite galaxy. That is the membership problem Laszlo was talking about. And the only way to tell them apart is using spectroscopy, as their spectra contain information about the surface gravity. However, it is hard to tell. This is what we see after a couple minutes of exposure. It's very hard to tell because of the noise. We have to keep looking at the star for several hours longer, because the longer the exposure time, the stronger the signal to noise ratio. And traditional methods takes hours to fit the physical parameters of stars. To be clear, it takes hours to get a spectrum, and it takes a couple minutes to do the parameter fitting of the stars using chi-square and similar methods. But the 80% of targeted stars are not interesting. The power of estimating the value of star from raw noisy spectra is highly demanded. And I don't want to stress you out, but it's an $80 million instrument, and it costs $100K to operate per night. We have less than 100 nights of telescope time. As Laszlo explained, the spectrograph has 2,400 fibers, meaning that we can observe 2,400 objects simultaneously, and we can move any one of the fiber to change target anytime. Here's some early stopping criteria that we want to apply to filter out unwanted stars. First, is this target a member? Like if it's the foreground dwarf instead of the target giant, we want to move on. And second, if after long exposure, the noise is still too large, we don't want to observe it to begin with. Like we don't want to observe it at all. And lastly, but a third point is that if we already get everything we want from the spectra, and we want to move on to see new stars. So to conclude, time is the most expensive factors in spectroscopy, and we need a rapid feedback loop to decide early on which star is worth continuing observation. So let's bring, because that's a very challenging problem, and with traditional method, we cannot quite solve it. So let's bring in the AI guy. And the modern machine learning is becoming increasingly important in science. We collect increasingly larger amounts of experimental data, but our ability to analyze this data has not kept up with the data avalanche. Machine learning, in particular, variants of deep learning are emerging as a promising way to overcome this barrier. So can we develop deep learning algorithms that optimize the target selection, especially can they process raw noisy spectra and do it better and faster? So recall that the traditional spectral analysis takes several hours. If we can train a neural net to estimate parameters from the spectra and train it to be stable under extreme noise, then we only need a couple minutes of exposure time. And once the neural net is trained, it takes milliseconds to infer. So the lower bound of the exposure time, the lower bound of the exposure time is the accuracy of the neural net. Is that accuracy of the neural net must be high enough for the screening process. Therefore, we can form a rapid feedback loop. So there goes this amazing idea, the AI telescope, a telescope in a feedback system powered by AI tools. Just like the self-driving car, algorithms will be making decisions to select stars for us. As you can see, there are two loops in the algorithm. The shorter loop is the rapid feedback loop, and the longer one, the rapid feedback loop we just talked about, and the longer one with a period of months is the adaptive feedback loop, which refined the selection algorithm for the rapid analysis. It will be implemented with reinforcement learning. We need that longer loop because the science case of the survey are complex and multi-pronged. The problems are more complicated by not knowing what data will shown in advance. So we must be able to refine our target selection algorithm to adapt any changes, and we want to update it in real time. So in science, we also need to understand that I have talked about our AI solution to our problem, but there is problems with the AI. So we need, if we are doing science, we need to understand and estimate the statistical significance of our derived results. And there is a general skepticism towards the black box techniques. So for data with large dimensions, the networks can get quite large, making training slow and cumbersome. As a result, serious attention is being given to the physics-informed machine learning, how we can use prior knowledge about underlying symmetries, geometric, and physical properties of the data to simplify network designs. Here are the results of the dense neural net trained on the metallicity. From the top row is the effective temperature, metallicity, then the surface gravity. We can see that the results is not that ideal for the surface gravity because it's very hard to, the information is very hard to extract from the entire spectra. That's why we want to find some ways to do better feature engineering. One of the important properties of the spectra is sparsity. Most of the pixels are noise, and only a few informative pixels lives in a union of subspaces. And therefore, engineering informative features can be very tricky. So currently, we are exploring several approaches to rank the pixels by their importance in parameter inference. That is to measure how sensitive one pixel is to the parameter changes. For example, the red shaded region, there is like 3 distinct lines. It's called the Gaussian triplet. And these 3 lines only appear in stars that has lower temperature, which is the red stars. If you have a blue star, you don't have these features. So these are the key informative features, and the scientists over the years have derived a list of the key line features called the Lick indices. But the list is short and not complete. The question is, how do we do feature engineering? One way is to analyze each pixel at a time, or each line at a time, but it is time consuming and computational intensive. On the other hand, we can analyze the entire spectrum altogether. But as you can, as I showed you the results before, the accuracy drops because the information are being washed away as lots of pixels carry mostly noise. Therefore, we need to find the sweet spots in between the two extremes. We want an algorithm that can first group the pixels that change together along the parameter space, and second, drop the pixels that carry mostly noise. And third, we wanted to do it automatically. And the algorithm that can do such magic is PCA, the Principal Component Analysis, which is a dimensional reduction tool. Let's see an example of principal component analysis performed on stars in the blue horizontal branch. So they are the very blue stars, and you will not see the 3 lines I talked about before. The data we use is the normalized Bose stellar models. Notice that the PCA is done on the log of flux, because since the log of the absorption lines are additive. So in the bottom panel shows the top 5 eigenspectrum or principal components of the stars. The first one clearly shows the Poisson series, which will tell us the effective temperature. And the second and third combined will tell us the log G, the surface gravity. And the 4th and the 5th, you can see the spikes in there. They are the metal lines.
Excuse me, sorry. We have a technical problem.
Okay, so this is an example of PCA performed on the stars, like the blue stars. So the data we use are the normalized Bose stellar models. Notice that the PCA is done on log of the flux, since the log of absorption lines are additive. So you can see basically the first PCs will tell us the effective temperature, and the second and third PC combined will tell us the surface gravity, and the 4th and the 5th eigenspectrum, you can see those spikes. These are the metal lines, so it can tell us the metallicity or the carbon percentage of the stars. Just to be clear, the figure shows the top 5 eigenspectrum or principal components of the stars. And an even better technique is called the principal component pursuit, or PCP. PCP is a method that makes the widely used statistical procedure principal component analysis more robust. It can decompose the data matrix into a low rank and a sparse matrix. It is widely used in computer science to separate the low rank background from the object of interest. For example, galaxies spectra can be viewed as composing of a slowly varying continuum and absorption lines, plus some sparse part of emission lines. We see that PCP does much better at extracting the sparse features than PCA. And there are some other projects we are working on, but I don't have time today to tell you guys. For example, we are building a generic model for the stellar spectra, which is the spectrum generator. And we are also building variational encoders on those intelligently engineered features, and also denoising autoencoders to get rid of the noise. We also apply these to aid the Bayesian hierarchical modeling, which Laszlo just talked about, for the actual target selection. We're also developing the reinforcement learning feedback loop for dynamically changing the target selection. So to conclude, my research is geared towards designing tools for the next generation AI telescope powered by deep learning techniques, augmented with insights from astrophysics, computer science, and artificial intelligence. Our work represents a recently emerging direction in AI, which instead of controlling self-driving cars, the AI is helping us to run our scientific instruments more optimally. With such powerful tool, we hope to tackle hard science problems. Yeah, thank you.
Thank you, Viska.
This is just because PCA will pick up the nonlinear features, and so if we apply PCA on non-normalized spectrum, it will pick up the overall shape instead of picking up those lines. So this is just an example to show you that what are these line features in the spectrum. That's why we use the normalized models. But for all the other applications, we use the non-normalized spectrum directly. Yeah.
Okay. Anybody else for the questions? I cannot see any raised hands, so thank you very much. Problem, and I hope maybe you can continue with us. So thank you very much, and let's thank again Viska.